All right, lesson 5. Lesson 5 comes from chapter 8. I know that page 300 starts in 8.4 and 304 stops in 8.5. It's kind of strange. All I need you to know is how to rationalize a simple denominator. So they actually start explaining that in 6.4. But we're going to put it in lesson 5 here. And all we're covering is the first little part of 8.5, not the rest of it. So this is all right here in one page. So students will be able to rationalize the denominator of a rational expression, only talking about the monomial radicals. So, monomial, one term polynomial, with variables. Okay, so right here, some rational expressions are written as fractions with radicals in their denominator. So there's some things you're not allowed to do in a fraction. You're not allowed to have a 0 underneath. That makes it undefined, right? You're not allowed to put a decimal in a fraction, okay? Another thing you're not allowed to do is leave a fraction unreduced. So you have to reduce all fractions as you come across them. Another thing you're not supposed to do is leave a radical in the bottom, in the denominator of a fraction, okay? So that's one of those other rules that we want to fix. So say we're working along on a problem and our final answer comes down to a square root of 6 over square root of 5. Well, that doesn't reduce away the radicals, so you're not allowed to leave it like that, okay? So we need to convert the square root of 5 on the bottom to the whole number 5, not a radical. So the way we do that is we multiply the whole fraction by itself, because think about it, the square root of 5 times the square root of 5 is the square root of 25 according to the product rule. Since they have the same index of 2, I'm allowed to multiply the radicands together to get 25. The square root of 25 is a 5, a whole number 5, okay? So whatever we multiply the bottom by the fraction, we multiply the top to make an equivalent fraction, okay? So if we multiply the top by the square root of 5, we're going to get the square root of 30. So the square root of 25 simplifies to 5, so our final answer, so apparently the square root of 6 over the square root of 5, an equivalent fraction to that with radicals in it, is that. Okay, so this got multiplied by the square root of 5, so this got multiplied by the square root of 5. That's how we got this. That's all you need to do to fix the radical in the denominator, which is the problem, okay? So if you're working on a problem and this is what's left, you need to multiply whatever is in the radicand by itself so you can get itself as a whole number. Whatever you do to the bottom, you do to the top. It's just a coincidence. This is a whole bunch of 13s, okay? But the square root of 13 times 13 is just that. But once you're here, notice what you have. You still have a fraction, excuse me, that needs to be reduced. So you're here. So believe it or not, this fraction with the radical in it is equal to the square root of 13. That looks very strange over 1, but that is true, right? Because this, I'm not going to do it again, but you can see it over here, okay? That's just the way these things are. So just follow the rules. So you're working through a problem and you're left with this stuff. So recognize the fact that you can reduce the numerical coefficients. If you divide both numbers by 6, you get 1 over 6. No, you don't. No, you don't. You get 1 over 2, right? Sorry. I'm getting ahead of myself. Right, 6 into 12, 1 over 2, same as half. Okay. So you can also think of this as 14 over 22, which can be reduced by 2 as well. So that's the same as 7 over 11, which is the same as the square root of 7 over the square root of 11. That takes into a lot of rules that we've been working on all together, okay? So this can be reduced to a 7, and this can be reduced to an 11 by 2, all right? So you're left with this fraction here after you reduce that, okay? Now, when I reduced it, I still had a radical on the bottom. I still have a square root of 11. That's the problem, not the 2. So I'm going to multiply by itself. That's going to give me 2 times 11, which will give me 22 on the bottom. Okay, made the radical disappear. Whatever I did at the bottom, I have to do the top. So the square root of 7 times 11 is the square root of 77. So that's going to stay there. That's my answer for that. Okay. And even if the x's are involved, remember this is still the same as this right here. All right, so the problem is the square root of 14. Multiply the numerator and the denominator by that. That gets me my 14 here. And then whatever this turns out to be goes here. And that's my final answer. It's not going to be... let's see, 154 is a large number. We want to check that there are no perfect squares in a 54 real quick. Is 154 divisible by any of our, just checking myself here, 54. If there's any perfect squares in a 54. There's, wait a minute, sorry. 154, I was looking at a 54. Okay, see, we have to do this too. We have to do this too, because we have to be right. So, give me a second. Any perfect squares in a 154? There is not. I'm just checking. So I can do that process, but really you should go back and look at what makes up. If 154, I'm just giving you an example. 154 is 11 times 14. 14. Think about it. That's an 11, a 2, and a 7. There is no squares of anything. It doesn't reduce. You do have to check. I mean, if there were 2 2s that came out or something like that, you can reduce the 14. But 154 doesn't have any perfect squares in it. So that is my final answer. Okay? You do have to check. It should have been clear. I should have thought back over here. There was no common factors. If there's no common factors in 11 and 14, there's not going to be when you put them together. Okay? Just wanted to check on that. All right, so all we need to do is rationalize these. So if that's the problem, then that's all I need to do to get rid of it. Okay. Let's reduce for a minute. Divide by 2, that's going to give me the square root of 9 of the square root of 25. Nicely convenient. That's going to give me 9 square root of 25. So that's going to give me 3 over 5. Now, what I could have done is the square root of 18 over the square root of 50 and multiplied by the square root of 50 over the square root of 50. That's going to give me 50 over, hang on, 18 times 50 is 900. 900, square root of 900 is, let's see, that's a square root of 100 and a square root of 900 is a perfect square. 900 is a perfect square. Sorry, fixing my key here. of 30. So 30 over 50, that reduces by 10, that gets to 3 over 5. So even if you forget to reduce first, you'll still get there. It's just you're working with much larger numbers than you need to. I think you agree that this way was kind of the better way to do that. Okay? All right, what happens if we throw variables in there? What's going to make that not a radical? Again, multiply it by itself. And whatever you do at the bottom, you do at the top. Right? So what is x times x is x squared. The square root of x squared is x. That fixes it. You're allowed to have a variable on the bottom, just not a square root. Okay? Square root of 17. Square root of 17 is going to be the square root of 17 over 17. That's okay, right? That doesn't reduce, right? That's a square root. It's only the square of 17, not 17. So it's less than that, right? That's not an improper fraction. You get it. You know what I mean. All right, square root of 3, square root of 3. That's the square root of 9. Negative 3 times the square root of 3, which is 3. Negative 3, 3. So that needs reducing, right? So final answer, negative square root of 3. I would put this together. Keep that x in there. When you reduce, that's going to be the square root of (4x), which is 2 square root of x. So what's the other way you could have done that? You could have multiplied by 2, because that was the problem, right? Perfect. Nothing wrong with that. That's going to give you the square root of 4 over the square root of 16x, which is going to give you, 2, 4 square root of x, and you reduce that and you're going to get your 2 square root of x. Okay? Either way, that works fine. That's it.